Hello, I am Ananthavalli. Welcome to this new video from Guidancee Education channel. We are starting a new chapter in class 12, that is plus 2 physics. Chapter 2, electrostatic potential and capacitance. In this video, we will be discussing electrostatic potential energy, definition, determination of electrostatic potential energy, and expression for it. We will also discuss electrostatic potential, definition, determination of electrostatic potential, expression for electrostatic potential. By the end of this video, you will understand clearly the difference between electrostatic potential energy and electrostatic potential. In order to help you get the concept, I have repeated a few points. Don't become impatient. Watch the video completely so that you get all points clear. And if you think the video is useful, like the video, share the video, leave your comments and also subscribe and support. Thank you. Come, let us start the class. Our topic is electrostatic potential and capacitance. In the previous chapter, we have already learned about electric charges and electric field. You already know that electric field is the influence of the electric charge all around itself. That is in three-dimensional concept. It is the force due to that charge all around itself. It is also equal to the Coulomb force. When another charge is kept in the electric field due to an already existing charge, that electric charge will experience a force. If it is a like charge, the force will be repulsive force. The repulsive force experienced by the additional charge kept, let us call it as test charge, represented by the small letter q, and the already existing charge as source charge, represented by the capital letter Q. Let us continue. The force is due to the electric field of the source charge and it is proportional to the charge on the test charge. Generally, the source charge will have a large magnitude of charge and the test charge will be having a minimal charge. This is adjusted so because the test charge or the presence of the test charge should not alter the charge configuration of the source charge, or the source charge should not be repelled away. The source charge should remain static, that is stationary at a location. If the test charge is given an external force, then the test charge can be made to remain in the electric field due to the source charge, overcoming the repulsive force due to the source charge. Under this situation, the test charge will come to possess an energy in itself. The energy possessed by the test charge is called electrical potential energy of the charge. The electrical potential energy possessed by the test charge will depend upon the distance of the charge from the source charge as well as the magnitude of the test charge. When we use the term electrostatic potential, we mean the energy of the location. When we refer to electrical potential energy or electrostatic potential energy, we mean the energy of the charge at that location. Energy of the location is due to the source charge. That is, electrostatic potential is due to the source charge. So there are two terms used: electrical potential energy of the charge and electrostatic potential of location. Both these quantities change from place to place. It is not at all difficult to understand or differentiate these two terms. The only thing is you have to follow the class thoroughly without skipping. Now that you have understood these two terms, I will first define electrostatic potential and then define capacitance. Electrostatic potential, represented by the letter capital V, is the energy of a location in the electric field due to a static charge. Capacitance, represented by the letter capital C, is the ability of a capacitor to store energy. Perhaps you already know that capacitors are gadgets used in certain electrical gadgets like fans, which increases the speed of the fan. It is specified that electrostatic potential is the energy of the location in an electric field due to static charge. Capacitors are instruments which store electrical energy. Now let us consider how we can determine electrostatic potential energy of a charge kept in an electric field due to a static charge. Consider a source charge, capital Q, remaining static or stationary at a particular location. All around this charge in three-dimensional space, the effect of the source charge is felt. That is, electric field due to the source charge is experienced. I have marked a few locations in the electric field of the source charge where the influence of the source charge is felt. Electric field at a location is the Coulomb force exerted by the source charge at that location. It is equal to Q by 4 pi epsilon naught R square. Epsilon naught is the permittivity of the medium and R is the distance of the location from the source charge capital Q. Capital Q is the magnitude of the charge. These locations are at different distances from the source charge, so the value of R will be different in each of these cases. In the formula for calculating Coulomb force, R is in the denominator. So as the distance increases, the force decreases. Now the definition for electrostatic potential energy represented by the letter capital U. It is the energy stored in the charge by virtue of its position in an electric field. Charges kept in different locations in the electric field due to a source charge will possess different amounts of energy. The energy acquired by the charge is called the electrostatic potential energy U of the charge at that location. We have already seen that the electrostatic potential energy of a charge at a location is equal to the electrostatic potential of that location due to the source charge. Therefore, if we calculate the energy acquired by the charge at a location, we can ascertain the electrostatic potential of that location. For that purpose, let us select one particular location in the electric field and determine the energy of a charge when it is kept at that location. Let us note this point as small p. Assume a test charge Q having the like charge is present at a location away from this location P. Let us mark that location as R. There will be an electric field at location R also, but it will be less than that at P. When the charge is at R, then also the charge will possess a certain energy due to that location. The energy possessed when it is at location R will be less than that of the energy possessed at location P. But we want to find out the energy acquired by the charge when it is shifted from location R to location P. Since like charges repel, this test charge will experience repulsion due to the source charge, whether it is at location R or at P. So, an external force equal but opposite to the direction of the repulsive force will have to be applied on the charge in order to shift it from location R to P. External force equivalent to overcome the repulsive force due to the source charge is applied bit by bit and the charge is moved towards P without acceleration. As the test charge has only a small amount of charge in it, it does not alter the charge configuration of the source charge. The charge is moved bit by bit slowly and finally it reaches the point P. The charge has moved from R to P. Let the distance from R to P be equal to R. So the external force causes the charge to cover a certain distance. So force into the distance covered becomes the work done in order to shift the charge from R to P. This work is stored in the charge as potential energy at each location. So the potential energy acquired by the charge at P will be equal to the work done by applying force bit by bit. The force is changing for each small distance in order to shift it from R to P. UP greater than UR. Under the influence of the external force, the test charge Q will remain at P. As soon as the external force is released, the test charge P will be repelled away from the location P. Its potential energy at P will be transformed into kinetic energy. Kinetic energy is by virtue of motion. Potential energy of the charge at P is the total work done on it. Let us make its representation. Work done is equal to Fs. F is the electric force equal to Coulomb force, which is equal to Q by 4 pi epsilon naught R square. When we consider the test charge also, the force between the two charges will be equal to capital Q small q by 4 pi epsilon naught R square. S is the distance R. PR is taken as capital R. Work done for the distance R cannot be taken as a whole because for each section the work done is different. So we have to split this R into so many small bits dr and we have to integrate the work done for each dr. So work done on the test charge is equal to Fr equal to capital Q small q by 4 pi epsilon naught R square R. Work done from R to P is equal to integrating from R to P force external dot dr. Capital Q by 4 pi epsilon naught R square is the electric field E due to the source charge. This can be written as integrating from R to P EQ dr. Integrating dr will be equal to capital R, that is the distance. This work done is stored as potential energy capital U at P. We can write it as capital U at P is equal to negative capital Q small q by 4 pi epsilon naught R square capital R. Work done is negative because it is in direction opposite to the direction of the repulsive force by the source charge. What is the change in potential energy at point P? It is the difference between the potential energy when the charge was at R and the charge at P. So change in potential energy delta U is equal to UP minus UR and that is equal to the work done, that is negative work done from R to P. So change in potential energy is equal to negative work done from R to P. Let us suppose the point R is at infinity. We have the freedom to choose any point. It is assumed that at infinity, the electrostatic potential is equal to 0 because the electric field due to source charge Q is assumed as 0 at infinity. Therefore, the electrostatic potential energy of the charge at infinity is also equal to 0. Then potential energy at P minus potential energy at infinity is equal to potential energy at P, because potential energy at infinity is equal to 0. Then that is equal to negative work done from infinity to P. So now we have found out the energy acquired by the charge when it is shifted from R to P is equal to the work done on the test charge to shift it from infinity to that point. Now that we have understood the term electrostatic potential energy of a charge, we will proceed to understand the electrostatic potential of a location. So we have the expression for electrostatic potential energy U of a charge is equal to negative work done from infinity to P is equal to negative capital Q small q divided by 4 pi epsilon naught R square capital R equal to negative electric field E into Q into R. Small q is the test charge of a certain magnitude. If this test charge is equal to unit charge, that is charge equal to 1, then work done is equal to negative ER. How is that? We divide negative EQR by Q so that you get the value of Q as 1. For considering electrostatic potential of a location, always the test charge is considered as unit charge. The amount of work done per unit charge depends on the electric field. This quantity is electrostatic potential due to the source charge at that location. R is the distance of the location from the source charge. I have already given a definition for electrostatic potential at the beginning of the video, but a more meaningful definition will be electrostatic potential capital V at any point in an electric field is the amount of work done to bring a unit positive charge from infinity to that point without acceleration against electrostatic force. You can rather give this definition as the answer for a question based on definition for electrostatic potential. How can we represent electrostatic potential? Change in electrostatic potential delta V between points P and R is equal to potential at P minus potential at R. This is equal to electrostatic potential energy of test charge at P minus electrostatic potential energy of the test charge at R divided by the charge Q. UP minus UR by Q is equal to the change in electrostatic potential energy of unit charge in that electric field, which is equal to work done to shift the charge from R to P divided by Q. Just as we did in the case of electrostatic potential energy of a charge, if you consider point R at infinity, change in electrostatic potential is equal to electrostatic potential at point P minus electrostatic potential at infinity, that is equal to electrostatic potential energy of the unit charge, that is electrostatic potential energy of Q at P divided by Q. We already know these values at infinity is 0. This is equal to work done to shift the test charge from infinity to P divided by Q. Remember, test charge is not unit charge. It has a certain magnitude. That is why we divide it by Q in order to make it equal to 1. Now, electrostatic potential Vp is equal to work done from infinity to P divided by Q. This is the work done to shift unit charge from infinity to P. The work done on unit charge in shifting it from infinity to the point P is really a state function. It does not depend on the path. It depends only on the initial and final position of the charge, that is infinity, and the location where we want to find the electrostatic potential. Capital Q is the source charge, P is the final position, and R is the initial position where Q is kept. This Q may be shifted from R to P through any of the routes that are shown in the diagram. Since electrostatic potential is a state function, it does not depend upon any of the paths through which the charge is shifted to P. It depends only on initial and final positions. If the video was useful, do like the video, share the video, and also leave your feedbacks as comments. If you have not yet subscribed, please subscribe and support me. Thank you very much. We will meet in the next video with another important topic. Till then, bye. Take care.